To explore higher and higher energies, particle physicists are in constant need of larger and more powerful colliders. It seems that size really does matter. But with the Large Hadron Collider now clocking in at 27 kilometers in length, how much bigger can we go before geographic and political constraints begin to define the new frontiers of particle physics? Fortunately, a couple of forward-thinking academics, James Beecham and Frank Zimmerman, have gotten ahead of the collider curve and know somewhere where there is plenty of unclaimed open space for a new machine. The Moon. For millennia, humans have looked at our celestial neighbour with a sense of awe and mystery, a constant companion jealously guarding the secrets of its far side and mocking our inability to reach out even into the shallowest depths of the wider universe. Most who have contemplated its pale, ever-present form, never daring to hope that one day we might visit this alien world and illuminate its secrets. However, today, in an age of spaceflight, lunar exploration, and extraterrestrial habitation, scientific exploration on the moon may not only answer the questions pondered by our long-lost ancestors, but prove to be an essential stepping stone towards unravelling the deeper mysteries of particle physics, the evolution of the universe, and even the very origins of the life on Earth the moon helped to seed and sustain. It seems that shining a light even minimally into the great void surrounding our planet could see that light penetrate far further than we can ever comprehend.
It's one small step for man, one giant leap for mankind.
The moon provides a vast, largely untouched wilderness where an ultra-high energy collider could be built and operated. After the discovery of the Higgs boson in 2012, and as the Large Hadron Collider presses forward into its second decade of operation, discussion has naturally shifted to the design and commission of colliders tasked with the exploration of unknown energy regimes far above those accessible at the LHC. Despite the success of the Large Hadron Collider, particle physics still holds many mysteries. The nature of dark matter, the vast preponderance of matter over antimatter, how gravity interacts with the other fundamental forces, and many, many more. Our latest mega collider has provided few, if any, hints as to the energy scale at which new particles and phenomena that underpin these mysteries may be producible and observable. The 21st century is often called the age of biology, or artificial intelligence, or robotics, the golden era of physics when the revolutions of relativity and quantum mechanics shook the world and the discoveries of elementary particles led to a string of Nobel Prizes, have passed. Nowadays, people worry about a desert scenario, where no new particles will be found for many decades to come, if ever. New particles and phenomena could appear at any energy up to the Planck energy of 10 to the 16 tera electron volts, the energy at which we know the quantum effects of gravity become strong, and 15 orders of magnitude above the current beam energy of the LHC. new, higher energy colliders, including the 100-kilometer Future Circular Collider at CERN, the Super Proton-Proton Collider in China, and even a future 2,000-kilometer collider in the sea, spanning the Gulf of Mexico, have already been proposed and promise to reach energies 10 to 100 times that of the current LHC. But as Hadron Colliders expand, geographical and geopolitical constraints become increasingly acute. We're running out of space. There's nowhere on Earth we can site them. Nowhere on Earth. The moon is a vast, untouched wilderness that humans are once again reaching out to explore and utilise. NASA, in collaboration with Elon Musk's SpaceX, plans to land humans on the moon in 2024 and establish a permanent human presence by 2028. Moon deliveries will soon begin under the framework of the Commercial Lunar Payload Services Initiative. As we explore the entire surface of the moon with human and robotic explorers, we will be able to survey the geography of the moon, determine the nature and quantities of raw materials that can be extracted from moon rock, and optimize the placement of future large-scale lunar infrastructures. A Hadron Collider, following one 11,000-kilometer long Great Circle of the moon, could be 100 times longer than the proposed Future Circular Collider, and capable of producing a collision energy of 14 peta-electron volts, 1,000 times higher than that of the current Large Hadron Collider. The US Department of Energy has already encouraged the worldwide particle physics community to collaborate in creating a sustainable and scientifically led presence on the moon, and it may be impossible for us not to answer. Unravelling the fundamental mysteries of the universe's tiniest frontier may be inextricably linked to exploring those of its largest. Commissioning a Hadron Collider in a low-gravity alien environment is a colossal undertaking, but not all aspects of the moon's environment work against us. Traditional proton colliders guide particles around the ring using high-power, ultra-cold, superconducting dipole magnets, the protons themselves being rotated in separate beam pipes at high vacuum so that protons do not interact with air molecules. Fortunately, the residual lunar molecular density of around 10 to the 12 molecules per meter cubed is at least 100 times better than the vacuum in the beams of the LHC. Charged particles could circulate between open, guiding dipole magnets without a dedicated vacuum system, shielding, beam pipe, or pumping system. Radiation produced by rapidly accelerating particles could also simply be allowed to escape into the surrounding moon rock, or even the lunar sky. Perhaps we'll become a tech signature for another inquisitive alien race. So, could we simply build the collider on the surface of the moon? Well, probably not. Temperature extremes on the moon's surface present a huge challenge for a Hadron Collider. Superconducting dipole magnets require the maintenance of incredibly low temperatures. When exposed to the sun, the temperature of the lunar day can reach 130 degrees Celsius, far above the temperature threshold at which superconducting magnets can operate. However, during the night, the temperature plummets to around minus 175 degrees Celsius, 100 Kelvin, roughly the temperature at which modern high-temperature superconducting magnets are capable of operation. It might be possible to charge an energy source for a moon collider during the lunar day and then operate the collider at night when the magnets become superconducting, avoiding the need for dedicated cooling systems and subterranean tunneling. However, such a scenario would suffer from several drawbacks. Lunar days and nights last for roughly half a month each, 13.5 days. The machine would be unusable for a minimum of half the time. We would also not be able to have the collider follow an entire great circle of the moon, as we would need to ensure that the entirety of the collider experiences lunar night at the same time. This would constrain the length of the collider and hence the energy it would be capable of reaching. Surface construction would also leave the collider exposed to strikes from meteoroids. Without a protective atmosphere, the lunar surface is constantly bombarded by small, fast-moving rocks originating from asteroids and comets. More than 1.4 tons of rock striking the surface each day, leaving craters from a few centimeters up to roughly 10 meters in diameter. Infrastructure constructed on the surface would therefore require heavy, expensive, and experimental shielding. These concerns could be reduced by digging a trench a few meters deep, installing the machine, and then filling the trench back over, a process known as cutting and covering. Apollo 15 and 17 measurements indicate that after you reach a depth greater than about 50 centimeters below the moon's surface, the temperature remains roughly constant and does not vary widely with the lunar day and night cycle. However, the absolute temperature 50 centimeters below the surface is roughly 255 Kelvin, meaning that a dedicated magnet cooling system would be required. Shielding might also still be required to protect from the largest meteoroid strikes. The method of construction of a lunar collider is clearly a trade-off of pros and cons, time and money, energy reach, and reliability, but it may be impossible, given the unique challenges of the lunar environment, to avoid significant deep moon tunneling. Regardless of the construction approach taken, boring through peaks and spanning over great depressions will be essential. Boring tunnels tens to hundreds of meters below the lunar surface would protect the system from meteoroid strike and create a constant temperature environment, although a magnet cooling system would still be required. Significant lunar excavation would likely increase construction time and cost, but may be able to take advantage of the planned development of lunar boring machines operated remotely from Earth, and plans to explore and utilize existing lunar lava tubes as locations for lunar habitation and scientific research. The construction of significant subterranean lunar infrastructure would require cooperation and collaboration with several other organizations and initiatives, but could benefit all. But which great circle of the moon would be optimal for a circular lunar collider? The moon's surface is incredibly rough, with the far side of the moon being far rougher than that which faces us. The maximum and minimum elevations of the moon relative to a sphere are plus 10.8 kilometers and minus 9.1 kilometers. These are comparable deviations to those found on the Earth, with Mount Everest standing at 8.8 kilometers and the Challenger Deep section of the Mariana Trench at minus 11 kilometers. But for a moon radius only 1/4 that of the Earth's, the moon is incredibly rough. When choosing a path for any collider, large elevation changes that create sharp turns in the path, demand drilling or suspension, and hinder maintenance and access efforts should be avoided. One appropriate path for the collider could be to use roughly the great circle that represents the edge of the moon as we see it from the Earth. Looking at a relative elevation map of the moon, this path avoids many, but not all, of the most severe elevation changes on the moon. This path would, however, pass through the Great Mare Humboldtianum, potentially requiring careful alignment of the dipole magnets on either side of the depression to allow the beam to pass over, fully exposed to the lunar sky. Determining the exact construction methodology and siting for a moon circular collider will require full use of the Unified Geological Map of the Moon, further information from NASA's Artemis program throughout the coming decade, and courageous decisions regarding what physicists and engineers believe they can get away with on the moon. Of course, a Hadron Collider is nothing without power. Charged particles accelerating around curved tracks emit substantial synchrotron radiation. The harder the turns, the more energy is lost. Higher power colliders must be larger so that their turns are as gentle as possible. The power loss of a collider scales as the relativistic gamma factor of the circulating protons to the power 4. The faster the particles are moving, the more energy they radiate and lose. The loss also scales linearly with the beam current. The more particles that are circulating, the greater the energy loss. In contrast, increasing the circumference of the collider only reduces the energy loss linearly. Taking the 4.8 megawatt synchrotron loss expected of the 100 kilometer long future circular collider and performing the relevant scalings for the Moon Circular Collider reveals that the latter will require a constant supply of around 10 terawatts to keep protons circulating at the desired energy of 7 peta-electron volts. 10 terawatts. For comparison, the total energy consumption of the Earth for the entire year of 2019 was consistent with a source of power 18 to 20 terawatts. We would require roughly half as much power to run a moon collider using contemporary techniques. NASA and the US Department of Energy have already begun studies of the deployment of KeV-scale fission reactors on the surface of the moon. However, even full-scale Earth-style fission reactors would not get us anywhere close. The 444 currently operational non-military fission reactors around the world generate a combined power output of around 400 gigawatts, meaning around 25,000 such reactors would be required to power the Moon Collider. Fusion power could be a useful alternative, but is in its infancy. The target power output of the upcoming ITER reactor is around 500 megawatts, meaning that again, 20,000 ITERs would be required to power the Moon Collider. Without phenomenal progress in the design and functionality of fission and/or fusion reactors, it seems that nuclear options are off the table. Or are they? There is another ancient astronomical fusion reactor that we might look to. The Sun. Thanks to the lack of atmosphere on the Moon, solar radiation is incredibly plentiful. The Sun produces a phenomenal amount of energy, 400 yottawatts, 4 times 10 to the 26 watts, enough to power the Earth 10,000 billion times over. That energy gets spread out over the surface of a sphere as it radiates away from the Sun. But taking the distance from the Sun to the lunar surface as 150 million kilometers, simple geometric arguments show us that roughly 10 petawatts, 1 times 10 to the 16 watts of solar energy, fall upon the lunar surface. Capturing just 0.07% of that energy would be enough to power the Moon Collider. If solar panels could capture all the solar energy radiated upon them, we would need an area roughly the size of Palestine or the US state of Delaware to be covered in solar panels, 6,000 square kilometers or so. Given that solar panels usually operate at around 20% efficiency, however, we would likely require a significantly larger region to be covered with panels, roughly the size of Belgium, 30,000 square kilometers. These solar panels could not be confined to a concentrated Dyson patch, as no part of the Moon is constantly exposed to the Sun. However, the panels could be arranged in a Dyson belt or band around the equator of the Moon, different panels receiving solar exposure and generating power as the Moon orbits the Earth. Such a Dyson belt could provide ample power for multiple lunar projects, as well as sending power back to the Earth. Such an idea was championed by David Criswell for many decades, and has been studied in detail by the Japanese engineering company Shimizu for their lunar ring concept, a ring of solar panels that could convert solar radiation to microwaves and beam almost limitless clean energy back to the Earth. Such a system would again require a much larger area of solar panels, perhaps as much as 1 million square kilometers, roughly half the area of Mexico. So in theory, we could power a Moon Collider, and in seeking to do so, tap into an incredibly abundant, constant, and green source of energy. Of course, the harsh radiation environment on the Moon provides logistic and technological hurdles to the widespread deployment of contemporary solar panels. Huge radiation exposure during the lunar day could severely degrade and damage solar panels, while meteoroid strikes remain a concern. These are known challenges that NASA is currently looking to address. It seems that, at least in theory, a circular collider on the Moon, utilizing only contemporary technologies, is feasible. Feasibility only strengthened by potential technological refinements and advancements over the coming century. The unique conditions of our heavenly partner offer a potential powering solution, And the lack of lunar atmosphere lends itself to several innovative construction scenarios, each with their own benefits, drawbacks, timescales, and price tags. As lunar exploration begins again in earnest, we need to ensure that we have considered the next steps in the road, how different lunar infrastructure and projects will interact, and how we can best work together to utilise the promises of our celestial companion. Next time, we will discuss the operating conditions for a moon collider, potential timescales for construction, and whether the moon's potential abundance of extractable compounds, ores, and elements might make the in-situ fabrication of collider components a more realistic proposition. I hope you'll join me again. Let's shoot for the moon. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.